Hello everyone, my name is Siham. I'm a PhD student at the University of Lille, and today I will present for you EXADPrinter, our semi-exhaustive framework for studying Android device fingerprinting. This work was done with Pierre Lapardrie and Walter Rudametkin. So, in today's society, Android occupy a very important place from a privacy perspective. Smartphones are used by billions of users. Majority of them are using Android devices. And Android users are interacting with a large variety of mobile applications, which made them primary target for user tracking. So to track Android users, we can use different techniques, varying from temporary identifiers that can be easily changed to persistent identifiers that are restricted to the system and privileged applications, or even personal identifiable information that are normally protected by permissions. While fingerprinting operates slightly differently, rather than relying on a single identifier, it combines many device attributes in order to create a unique identity. So, for now, most of fingerprinting research has focused on the browser side. Inside the browser, a website can access device attributes through the browser APIs. On the other side, a native application can access native APIs directly. So we can say that applications have much larger fingerprinting space than websites. And this leads us to our main research question. How much information can any third-party application access on a device without requesting permissions? To answer this question, we proposed EXADPrinter, a framework for extracting the maximum of information from a device without requesting permissions. This framework is composed of three main stages. We start by exploring the Android domain. Then we extract the device attributes. After that, we try to analyze fingerprints that we collected from real Android devices. So the first step was scrapping the Android documentation made for developers in order to get the list of documented classes that will be used the next stage for exploring those classes. Next, we combined three extraction techniques in order to extract the maximum of information. First, we executed 41 shell commands. Second, we leveraged Java reflection in order to explore the collected classes by inspecting those classes and invoking methods that are in the classes. This process is quite complex since it requires instantiating classes and also resolving parameters of the methods. After that, we accessed the content of three content providers, the settings global, system, and secure. Then we have implemented this extraction technique in the Amionic Android application that we have deployed on the Google Play Store since October 2024. This application doesn't require any permission except for the internet that we have used only to transmit fingerprints from the device to our server. And before starting collecting fingerprints, we did a pilot study with our team members, and we were surprised that we could collect some emails. So we have asked for the IRB before starting a large data collection. And as of December 2025, so after 13 months, we could collect 4,004 fingerprints from 3,143 devices, spanning on 9 Android versions from 8 to 16, and 69 manufacturers. EXADPrinter also allowed us to extract large fingerprints with more than 200,000 attributes per fingerprint. Then we try to analyze our fingerprints. The first thing that we asked is, are there any sensitive identifier that we could collect? For that, we considered 7 identifier types: emails, emergency contacts, MAC addresses, and some persistent identifiers. We have used regex-based filtering and also some access channels that are reported in the literature. And we could uncover more than 100 access channels that are leaking user identifiers. For now, about 20% of the devices in our dataset leak at least one unique identifier, with the MAC addresses and emails are the most leaked ones. We have disclosed those issues to the concerned parties, and we try to engage with them for the resolution. To illustrate some examples, we have issues that are related to the OSP itself. Like, for example, these settings which leaks the MAC address of the connected headset, or there are some leaks that are related to the vendor customization. Like, for example, these settings that on Xiaomi devices that leak the emergency contact of the person, and also we got some email addresses from some Samsung devices. Next, we wanted to know if we don't use any of these sensitive identifiers, how we could identify devices. For that, we have filtered out all those identifiers, and we tried to evaluate the remaining attributes using those metrics: the number of distinct values that an attribute can have, the number of unique values, and the Shannon entropy to evaluate the overall discriminating power. And here are some relevant examples. For instance, we have the system absence, which is the time that you last time rebooted your device. It's almost unique for all the data set, since it's like very precise. It's like the second precise. When combining it with the number of times that you have rebooted your device, this combination becomes more unique and can be used for short time tracking, since it could be not stable over the time. And when customizing devices, like, for example, changing the device name or changing your device ringtone, you become more and more unique. Also, there are some attributes that leak some information about the user behavior or habits, like, for example, the next alarm time. And there are attributes that leak information about the network or the connectivity of the device. Now, high entropy attributes alone is not sufficient for doing reliable fingerprinting. In addition to being discriminative, an attribute should be stable also over the time, which means that his value should be the same across repeated collections of the fingerprint. For that, we computed stability of fingerprint on each device individually. Then we tried to select attributes that are stable on 90%, 95%, 99%, and on all the data set. And we tried to find the minimum combination of attributes that leads to the maximum of uniqueness. So this graph shows how uniqueness evolves as we combine attributes. The y-axis is for the number of combined attributes, and the y-axis is for the number of unique fingerprints. As you can see, the curve also applies different stability constraint. As you can see, when we apply restrictor stability constraint, more attributes are needed to identify devices. For instance, with attributes that are stable on 90% of devices, we need only 6 attributes to reach full uniqueness. And even when being very conservative, by considering all the attributes that are stable on all devices in our dataset, we can reach near full uniqueness with only 28 attributes. So we can say that small sets of stable, permissionless, and discriminative attributes leads to identifying all devices in the dataset. So, to conclude, we have proposed a framework for doing permissionless device fingerprinting. We have collected large fingerprints that contain more than 200,000 attributes per fingerprint. We assessed the fingerprintability of the Android ecosystem, and we proved that user and vendor customization leads to more uniqueness. And we also showed that for now there are too many identifiers that are not protected by default. You can install the application by scanning this QR code. And thank you for listening to me, and see you in the poster session.